All right, inverses. You're going to find out why we did one in particular of the symmetries earlier, because it's going to prove important today when we talk about inverse functions. Pretty much the easiest thing to say for an inverse function is the domain and range basically switch, which in other words mean take x and y and switch them. All right. So for this very first one right here to find, you could say this is y equals x to the third, right? So y equals x to the third is one way I could look at that. And so what I'm going to do is I'm going to find the inverse of that function. Okay? Or in other words, what would cancel that out, right? That's what multiplicative inverses are, right? And so what we do is literally you switch where x and y are. So that was a y right there, so in place of it I'm going to put an x. That was an x right there, so in place of it I'm going to put a y. But you see how the third power stays? Everybody see that? Okay. And so now, though, when you get this, you still want it solved for y, which means you want the y all by itself. The y is not all by itself. It's got that big 3 up there. That's how we're going to get rid of it. Ooh, somebody said it, cube root. I've been told in the past to do a square root. Do you understand that a square root would not cancel out a cube? Right? But a cube root would. And again, house of I is kind of how I used to teach that. Right? And sometimes you write it that way. For just notational purposes, sometimes the inverse when we're within a problem is written like that, so that I know this one down here is the inverse of the one I started with. It's just to the negative 1 power. It's just kind of a notation, but then some people think, oh, that means 1 over y, and then weird things start happening, right? And so sometimes I don't do that. I just notate, well, that's the inverse. Okay? So again, the domain and range, or the x and y, have been flipped. So that is the inverse of that. And do you agree, those two, cubing something and taking the cube root, are actually the opposites of each other, correct? They would undo each other, right? So let's take a look at what these graphs might look like, actually. Okay. So here is your x to the third. Right, that's a parent graph. We should know that one, correct? So there is y equals x to the third. And here is, whoops, I missed a little bit there. There's your cube root. Do you believe those two to be symmetric to each other? Yeah. They have symmetry with respect to which line that we covered earlier? Not the origin, but close. The y equals x line. This green one, if I take this point right here and I go directly to that line, right, like we did in geometry, and I go directly out the other side, you see how I end up at that point? Okay. How about I start at this point? Okay. So inverse functions will be symmetric to each other with respect to the line y equals x, which is one of the main reasons that we talked about that one earlier in the chapter. Okay, so it just flips it over that line, basically, is what it does. Okay. Questions on the first one? Did you want me to give you some time to put that graph in, or you good? Put it in later? Okay. All right, this one's a little bit more complicated. So we have to find the inverse. Well, let's do it. What do we do to find the inverse again? Switch domain and range, right? And so we do that by switching x and y. So this was a y. So turn it into an x. That's an x right here. So turn it into a y. Do you notice how everything else remains? What do we got to do yet? We've got to solve for y. We would like that to be alone. It is not alone. So what's probably a good first step? We could square root, but then we have to square root this entire right side and then the entire left side. So that might not be a good idea. It will be in a second after I do something else first. Yeah, add the 6. Get that out of here. So minus 6 plus 6, that cancels. X plus 6, I don't really know what that is, so we'll write it as x plus 6. And then it's y plus 4 quantity squared. So again, when you take the square root of equations, you have to take it of both entire sides. You can't just take it of pieces. Okay? And so now it's taking the square root, much better option. Falsifies. So it's the square root of x plus 6 equals y plus 4. And we're almost there. not quite solved for y, but we're really close. Minus 4. Now, here's the tricky part. A lot of people like to line it up that way, right? So they see the x plus 6 minus 4 on this side, and all of a sudden it becomes x plus 2. But if you that plus 6 is in the radical. Okay, so you can't quite do that, so we have to keep them separate. So the x plus 6 stays, and then minus 4 is our inverse, because plus 4 minus 4 I can actually cancel. I was kind of hoping somebody would say something, but yes. Can I make it into... not quite. The question is, can I make the 4 into a 16 by squaring it, obviously? And then can I put it in there? No. If I was multiplying, I could. When you multiply radicals and they have the same root, like square root or third root, then you can put them together. But when there's subtraction, you can't. Okay, good question. This answer is, unfortunately, half right. This is half of the inverse. What's the other half? Yes? Yeah, we took the square root in this problem. We were the ones that decided to make this move. And so what should be out front of this square root? Positive, negative. Okay. So y equals positive and negative. But wait a minute. The positive is just the regular graph, and this is a parent graph. We should be able to do this one, right? It's the square root graph moved left 6 and down 4. What's the negative out front do? It just takes that graph and reflects it, right? Okay. And what did we start with? We started with some, can we graph that one? X plus 4 squared minus 6? Yeah, it's the parabola moved left 4 and, so if it's a parabola, when I flip it over the line y equals x, it should kind of almost look like a C, right? But if you only have the positive on this square root, do you get both the top and bottom of the parabola? You only get that top part, right? Because the square root graph only does that, correct? That's all that does. But if you do positive and negative, there's that parabola. Okay? Okay, so this one here in blue, wow, that was terrible. That one there in blue is which one? The original or its inverse? Yeah, it's this one right here, right? Okay. And then in green, that one right there is which of really the two I have written down there. That's the positive one, correct? And then there's the negative because it is reflected. All right, see all that stuff kind of coming together there? All right. And then it does actually have symmetry with respect to that. It's just reflected over that line. That's all it is. Okay. So that's one really good way to check if you actually have the inverses to graph it. Is it a reflection over that line? And if it's not, then you didn't do it. And all of it boils back to that symmetry that we did earlier. So based on this, which two of your parent graphs are almost inverses of each other? Almost. Not quite. None of them? Well, perhaps that'll be a question later then on an assignment. Which two are x squared and negative x squared? Nope, not quite. Yes? Nope, not the absolute value graph. Yeah. Hannah? Tough one for me to answer that one. She said y equals 1 over x. Not what I was looking for. Okay. How about y equals x squared and the square root of x? Are almost inverses, except it's only the positive square root. We would need the negative square root on there for it to be the actual inverse. Okay. So here, do you remember way back in probably Algebra 1, maybe even 8th grade, to test if a graph was a function? If a graph was a function, what you used to use, for example, if I gave you this graph, and I want to know, is that graph, that's really good, by the way, is that graph a function, you would use the vertical line test, right? You remember that? If the vertical line hit it more than once, it wasn't a function, correct? Okay. So now what I want to know is the inverse of these a function? So what you could do, there's two things you could do. You could say, all right, well, if that's what the original is, the inverse would be the reflection over this line, right? And so the inverse would be looking something like that, right? And then do the vertical line test, right? Or what we could do is, why don't we just reflect the vertical line over that and just do that test? So what happens if you reflect a vertical line over that? It becomes a horizontal line. Okay. So if I want to test if this one right here is a function, which do I use, vertical or horizontal? If I want to test this one right here, I use vertical. What if I want to test if its inverse is, use horizontal? This one, the inverse of this one, is not a function. How about this one itself? Is this one a function? Yes. How about this one itself? Is this a function? Yes. Vertical line test passes. How about its inverse? Yeah, we're good. Right? Some people worry about this spot right here, but it does gradually keep rising, so we're good. Okay. Okay. How about this graph right here? Is this a function? Yeah, vertical line test is good. How about its inverse? No, because the horizontal line test fails. Okay. So if we are to answer these, so determine the inverse. This one was, the inverse is no. How about this inverse? Yes. This inverse, no. Is everybody clear on which test to use? Yes? Okay, if you use the horizontal line test on the original, it means the inverse is or is not a function depending on if it passes or fails.
Yes.
You're testing the inverse.
Right. If it passes, it'll go through. It'll still go through once.
Exactly. Yep. If it passes through just once, you're good. So if it hits twice, no good. Hits once, good. Okay. Any other clarification on that? Okay. That's it? We're done? Awesome. Any other questions? Okay.